All right, you can go ahead, Chris.
Hi, good evening, everybody. Welcome to Hermanus Astronomy Club Center. Chris Engelbrecht. It's a real privilege to have you on our presenting a paper or a presentation to us tonight. I used to know him quite well from the meetings of the South African Institute for Physics, where we used to give lectures in the astronomy and space science group. I actually know his father much better than himself, because I met his father at the University of Stellenbosch, where I was a student or in my PhD year. So Chris comes from an astronomy background, even in his family. So it's no real surprise that he also ventured off into a physics and astronomy direction. But anyway, very well, most welcome to us. And we're looking forward to how you're going to encourage the signals from very variable stars to make them confess and reveal their inner secrets to us. So Chris, many thanks, and over to you.
Thank you so much, Peter. I appreciate that. I think to avoid feedback between my loudspeaker microphone, I'm just going to go to my headphones, because then I'll start the presentation. So let me just get the headphones on. So I can hear if there's a question. And I think what I needed to do is do that before the time. But okay, if there's interference, just let me know. So thank you for the opportunity. I appreciate it. Thank you so much. Always a pleasure speaking about things that I love. And as I was saying earlier, when I connected with Derek, I've tried to prepare a talk that will be accessible to everybody to some extent. So it's not a specialist talk, although there will be a few things for the specialist as well. But I've tried to make a general talk that everyone will get something from. And it won't take me an hour, so I hope if there are questions at the end, there'll be opportunity to also handle them. Okay, so I've titled the talk. There are various formats that got communicated, but it's all about astroseismology, which, as you can probably infer from the structure of that word, it is about vibrations of stars, just like we use seismology for the Earth. And there has to be an E. This was a long debate in the 70s. The fourth letter must be there. It's asteroseismology, and it's the vibrations of the stars. In other words, the music of the stars, right? Because music is nothing but vibrations. So I'm going to start my slides by just pointing at this photograph that I'm very fond of. This was taken on the 7th of March, 2009. And it's the launch of an astronomical satellite. And I'll tell you more about it later. But it plays a central part in what I have to say today. And I'm going to structure my talk around 4 aspects of astroseismology. Firstly, the basis for it, which will be very basic, but I think it's important to be aware of that. The history, so how astroseismology has developed. The revolution in astroseismology, which has everything to do with the previous image of that satellite being launched. And the last slide or 2 will just speak about the future. So I'm going to spend a bit of time just laying the table, and I'm going to go very far back. Plato lived more or less 2,300 to 2,400 years ago, and I don't know if this quote is real. I wasn't there to hear him, but this is attributed to Plato, and I think all of us here would relate to that. Astronomy compels the soul to look upwards and then leads us from this world to another. And that sense we get when we're under the night sky about this universe we're part of, and yet it's also this wonderful other place. And this desire of humans to understand what is beyond us has been with us probably forever, for as long as we've been able to think. And it has been expressed in various ways. This very famous woodcut, which you might have seen, probably will have seen, is falsely attributed to Dürer, but it's not. It was probably made in the late 1800s. But it's a beautiful rendition of this instinct we have as humans of wanting to know what is the mechanism behind this world we see and touch and feel. And there you can see an imagined, clockwork behind, which is informed by, the epicycles and those theories from millennia before. But it encapsulates our desire to transcend the barriers that our five senses present to us and understand more. And of course, the sense we have to use is the brain. And with the brain, we can travel further than the senses show us at first sight. So you'll all be familiar with this, I think, and that is that sound, as we hear it as humans, has a very mathematical basis. If you take a simple string, for instance, so that the top, never mind the small print that you can't see, it says first harmonic, and in brackets it says fundamental. But if you take a string on a guitar, for instance, or on a violin, or anywhere, and you fix it at the two dark black spots, if you hold it down there with your fingers, for instance, and you pluck the string, it will make a certain sound. And the vibration of that string, after you've plucked it, that you can see there with those dotted lines, that's just presenting the vibration of the string, is called the fundamental mode of vibration, but it's also sometimes called the first harmonic of the sound made by the string. If you then fix the string halfway through the initial 2 points, as you can see in the second picture from the top, it will still vibrate, but it won't move at the center. That's called a node. We'll speak about nodes later. And it will make a higher pitch of sound. If you've ever played a stringed instrument, you'll know that the shorter you make the available length of string that can vibrate, the higher the pitch. And you can have 3 sections, as you can see in the third picture, and then even 4 sections there. Now, Pythagoras, if you go back 250 years even before Plato, Pythagoras was fascinated by what we call the harmonic series. You can see there the fundamental string split into 2 parts, then 3, and then 4. And the Pythagoreans, and I'm not an expert on them, but maybe some of you are, but you have probably heard about them. They had this order. There were various levels of the order. There was the inner order and the out, they were the really core people in this order, and the ones who were not quite at the core yet. And there were rituals, and there were dietary habits. There were philosophies. It was a cult in a way. And they took on this figure here, which is the tetractys. I don't know if Pythagoras invented this, but anyway, if you add up those dots, you see there are 10. So it's 1 at the top, then 2, then 3, then 4. Those numbers add up to 10. And so numbers have always fascinated humans. Well, not all humans, but they have fascinated some humans also since time immemorial. And Pythagoras believed that the numbers 1, 2, 3, and 4 were in a way more sacred than the others. And it turns out, because he inspected what you could do with music, that if you take that string that I showed you before and play that note and the note when you split the string in half, those 2 notes are separated by an octave. And if you take the notes generated by the 3-fold separation and the 4-fold separation, and you play them together, that is a fourth, as it's called in musical circles. I'm not an expert on music either, but if you go to piano and you play a C key and the F just above it, you'll hear the fourth. And these are all pleasing sounds. And there are more, there are fifths and other things. And he found that there are very simple numerical relations between the notes, basically, that we as humans find pleasing. At the same time, people had realized by then that the planets, the sun, and the moon are the 7 bodies that move through the sky differently from the stars, as all of you in this club will know. And there were patterns, and people built monuments and timekeeping devices that you'll all know about to check the arrival of the equinoxes and the solstices, etc., and use that for all sorts of purposes, including practical things like agriculture. So there was this sense of numerical patterns connected with music and connected with patterns in the sky. And people like Pythagoras, he had the spoke of the universal music that the planets made, but we couldn't hear them, and they had a theory for why not. But actually, the type of mathematical structure that I showed you 2 slides back determines how different musical instruments sound to us. So there, very simply, are the patterns created in a flute, and I'm not sure which type of flute anyway, and in a violin. And the numbers there are essentially the number of sections that I showed you in those slides. So 1 up to 8 represent for the violin, then the string being split into more and more sections. For the flute, it's what you do by pressing your fingers on the holes along the flute. You break the air column into sections that can vibrate on their own. And you can see that the height of those red lines show you the strengths of the different harmonics. And depending on how the relative harmonics are amplified or not amplified, damped, you get a particular sound. And it's very simply mathematical. So, and I'll say more about this in a moment, the nature of the sound heard from a musical instrument depends on the structure of that instrument and how you are playing it. For instance, by using your fingers to press the strings on a violin or to press in the holes of a flute. What many people do not realize is how unbelievably sensitive the vibrations that are amplified and those that are damped, that are suppressed, how sensitive they are on very, very precise, very microscopic details of the structure. And I'm going somewhere with this, as you'll find out presently. On the left, sorry for my voice, on the left is a couple of photographs of a violin that was made by Stradivarius, the master violin maker many centuries ago. On the right is 2 images of a violin that you can buy at the shop shown there, Lane Violins in New York. Very good shop. And I've just made the images of equal size. So the design is the same. I mean, they're both violins. They both were made by people who know their art. And they were tried to, well, the people who made them tried to make these instruments as close as possible to perfection. And yet, if you take a master violinist and ask her or him to play a particular piece of music on first the one violin and the other, if you have a good ear for music and you close your eyes, you'll be able to tell which violin is being played. The sound from those 2 violins will be different because no one has been able to emulate Stradivarius again. And the tiny microscopic changes in his art of making a violin are detectable to the human ear. If we invert this, it tells us that we can listen to sound and make deductions about interior structure. And that is what astroseismology is all about. It's listening to the sound that stars make and inferring the interior structure. Now, people often jump up and say, you can't hear sound in space because there's no air. Yes, but sound is vibration. And when a star vibrates, and I'll show you more detail later, the light it emits changes in subtle ways. And with telescopes, we can measure that light extremely precisely in 2 ways. We can look at the entire light output from the star, that is called photometry, as many of you will know the difference, or we can send the light through a prism or interference grating and we can get a spectrum. And those 2 ways of measuring the light coming from a star give us an unbelievable amount of information about small physical events happening. And what has happened in the last decade especially is that we have been able to use the light coming from the stars as they vibrate, just like a musical instrument's components vibrate, to infer astounding things about them. And that is what I'm going to be talking about. So this was the foundation of astroseismology. I thought I'd just throw in Kepler there because you'll see later why. So as I said, about 1800 years after Plato and the early 1600s, he also was looking for this mathematical pattern. And while he was giving a lecture as a young man once at a college, and he was drawing Saturn, I don't have the diagram here now, but Saturn and Jupiter at opposition, it struck him that the actual physical sizes of the orbits of the planets, if you assume the Copernican system, which he did, where the sun is the center of the solar system, that they match the 5 solid figures that you get by making a three-dimensional figure out of similar surfaces. So you can see there is a cube which consists of 6 identical squares. You take 6 identical squares, you can make a cube. 4 identical isosceles triangles, equilateral triangles will give you a tetrahedron, and so on. And there are only 5 such solids which Plato had actually defined. And he found that these 5 perfect solids exactly matched the relative size of the orbits around the sun. So for someone in Kepler's time, that could not be a coincidence. And he developed a philosophy also, which he called the harmony of the spheres, trying to explain why this would be so. And there you can just see the model that Kepler made, and on the right-hand side is a blow-up of what you can see in the center there. And the 5 visible planets besides the Earth, people sometimes say there are 5 visible planets. Of course, there are 6, because you can see the Earth as well. But anyway, the other 5, he could then match with these solids. So again, that's an expression of our desire, our drive to try and make sense, mathematical sense of what we see out there. The year after Kepler published his laws of planetary motion, which had all been derived mathematically based on the wonderful observations of Tycho Brahe without any telescope, and that's a topic for a whole lecture on its own. Galileo published his Sidereus Nuncius, which is in English translated as the Starry Messenger, and with his telescope, he totally opened up the universe to us in a way that had never been done before. Now, getting back to the ancients, one last thing about them. Euclid, as you know, put down the elements of Euclidean geometry. Pythagoras, of course, gave us the Pythagorean law for right-handed triangles. And this simple geometry has played an astoundingly important role in what we know about the universe today. And I'm just explaining it here with the example of the use of parallax. Again, maybe all of you know about it, but if you do, then enjoy the pictures. The upper diagram shows the Earth's orbit around the sun. And you can see that a star right at the top, it says star, there's a red star, is observed from the Earth in January on the left, and then in July on the right, in that black diagram. And you obviously see the star superimposed on the stars that are much further away, the background stars as they are indicated there. And if you took a photograph, it might look like you see the 2 bottom panels show you. There's the red star seen in January and in July. Now, the background pattern has not changed. If you look at the white dots, they're exactly where they were. It looks slightly brighter on the left, but the positions are the same. But the red star has moved. And that is because it's nearer than the background stars, and the line of sight is different in January and July. And through simple geometry, if you can measure the angle called P in that triangle in the upper diagram, and we know the distance between the position of the Earth in January and July, which we also know, by simple geometry, you can get the distance to the star. And that is the method of parallax, which, of course, the Gaia mission is now taken to, I think, 1 billion stars or so. Hipparchus, 3 decades ago, more or less, 2.5 decades ago, a few 100,000 stars were given exact geometrical distances that way. Now for Gaia, we've got 1 billion, and that's wonderful. And so with this method, people started determining the distances to certain stars. And if we now jump ahead almost 300 years from Kepler to the early 1900s, we had women working in the US in various observatories doing extremely hard mathematical work, a very ingenious work, but because they were women, they weren't given the credit they deserved. One of them was Henrietta Swan-Leavitt, and she was given the task, very, very hard slog of work, to take photographic plates taken of the Large Magellanic Cloud in this stunning image. I've forgotten where it comes from. I normally credit things, but I didn't now. There's an image of the Large Magellanic Cloud beautifully. And she had to take these plates and determine the magnitudes of the stars on the plates by measuring their sizes on the plate, and very meticulously, and then finding the mean magnitude. So we're logging, setting up a catalog of these stars. So there is one field in the Large Magellanic Cloud from that survey, this photographic plate. And I'm going to show you another one. See if you can see a difference. I'm going to go up and down, up, down, up, down. You see the little winking light? Okay, so I'll show them side by side now. There's a row of 3 stars on the right, and you can see that the central one is much brighter on the right than the left. And as they kept on analyzing the plates, they realized, she mainly realized, that it winked on and off periodically. And eventually, she found many such stars. And that is what happens if you plot the magnitude of that particular, well, one of those stars over time. Is that you can't see that clearly, but from left to right runs a period of about 10 days. And you can see the magnitude changes by quite a lot. I'll show you a better picture in a moment. And she then started, totally of her own accord, finding more of these stars and making a graph of how long that repetitive cycle lasted. You can see there's a cycle that it's about 5 days there. And what is the extent of change in the magnitude between the top and the bottom, between the brightest and the faintest? And if you plot them, so that's a plot of about 20 to 30 stars. Period now runs again on the horizontal axis from 0 to 130 days. Minimum and maximum magnitudes are shown there. So of any vertical line there, you can see the black dots in squares just beyond 60 days, near the top of the figure. And those black dots show you the magnitudes at maximum and minimum brightness. So the lower magnitude, obviously brightest, the higher point. And then there are dozens of other little pairs of black points. So there seemed to be some pattern between the magnitudes and the period. And when she plotted that, the magnitude, of course, is the logarithm of the intensity, the base 10 log of the intensity. If she also took the base 10 log of the period, she found this. So a bit of a zigzag path, but you could fit a straight line through there that didn't seem just random. And so that is where the power of pulsating stars was first realized. Now, remember, these stars were all in the Large Magellanic Cloud. So their distance from us on Earth was almost the same, because the size of the cloud is much, much, much smaller than the distance to the cloud. So even though these stars were distributed throughout the LMC, the Large Magellanic Cloud, excuse me, relatively, they were almost the same distance from us. So this was real. These apparent magnitudes told us that the real magnitudes, the absolute magnitudes, were dependent on period for these stars. A more modern version of Henrietta Leavitt's first graph is here taken from the OGLE database, ongoing survey running in the northern southern hemisphere. And what they have up there is, again, the apparent magnitude for some of these stars in the Large Magellanic Cloud. And you can see with the advances over 90 years, the precision has become much better. And there's clearly a very, very close linear relationship there. This is what the prototype of this type of star looked like in 1908. This is a paper by Stebbins. You can go and look it up if you like. And the circles there are taken over many, many, many years, but they phased with a period. And that is what I'm sorry, for some reason, my throat's a bit dry, but I'm going to take a swig of water every now and then. That pattern, that steep ascent, and then that slow decline with the bumps is repeated again and again and again, approximately every 5.5 days. And all the stars that show this type of behavior are called Cepheids, after the prototype Delta Cephei. Soon after this discovery was made in both the LMC and the SMC, other people started looking for stars like this. Here's a plate that Edwin Hubble studied in the 1920s, more or less. This is M31, of course, Andromeda Nebula, Milky Way's neighbor. Well, not neighbor, but its sibling, its twin sibling in the local group. And right at the top, there are two little short black lines, and it says VAR, a bit of a smudgy writing, but VAR exclamation mark. He'd found a star that behaved like this in M31. That allowed him to get the distance to M31, because the pattern that Henrietta had found there, which was refined more and more, told you immediately, once you knew the period, what the real magnitude, the absolute magnitude was. And so therefore you could get the distance, because you got the apparent magnitude from observing the star, you get the absolute magnitude from checking its period, and voila, you have the distance. And so in 1929, in the Proceedings of the NAS, which is still a very active journal, Edwin Hubble wrote this paper, A Relation Between Distance and Radial Velocity Among Extragalactic Nebulae. So he'd been able to find Cepheids in various galaxies close to the Milky Way. And that, of course, was the birth of the distance scale of the universe. 70 years later, a large team of people, including the late Michael Feast, who until recently was obviously director of the SAAO for a long time, and then at UCT as an honorary professor, was on the team which used the Hubble Space Telescope to look for Cepheids quite far out. So here's M100, and you can see I just blown up the central core into the main Milky Brown picture. And then on the right of the Milky Brown picture is a small square, which has been zoomed into the left to give you that sort of jittery, pixelated picture in the center. And that star at the center of that box, now in black and white, is a Cepheid. And based not only on that star, but on many, and you can see 17,000 parsecs away, so that's more than 50 million light years away, based on Hubble observations of Cepheid stars in galaxies quite far out, up to I think about 100 million light years, a long-standing war in astronomy that had lasted for decades. And I was a very young astronomer. Many talks people gave was about this war. And the war was about the distance scale of the universe, about the Hubble constant. And there was the group aligned to Alan Sandage, who insisted that the Hubble constant was 50 kilometers per second per megaparsec. And all the observations they got and that they interpreted, they made to submit to their theory. And then Gerard de Vaucouleurs in Canada insisted that no, it was 100 kilometers per second per megaparsec. And everything he did and his team did proved, in inverted commas, that it was 100. They couldn't both be right, but there were strong figures in astronomy, and this war went on. And only with the Hubble Space Telescope, it turned out what he would have expected. If you take the log of 50 and the log of 100 and the log of 67, it's bang in the middle. So they were both embellishing the truth to fit their theories, which is a lesson for science. And now it's still a bit uncertain, but the number is somewhere between 67 and 72, according to the most current research. And that is a slide I threw in for Derek's cosmology group, how pulsating stars, which is what I am talking about today, gave us the first very, very essential jump to the distance ladder. And then you can see there in the center of this picture, it says galaxies hosting Cepheids and type 1a supernovae. And then you can use those galaxies to jump to the much further rungs on the distance ladder. Then you get other mechanisms that Derek has obviously spoken about and the group has spoken about in cosmology. But so that very simple observation of the connection between period and absolute magnitude led us to these cosmological conclusions. So that was done by using the Cepheids. But there are many other types of vibrating star. So there's the HR diagram. So it's in this case, it's a color magnitude diagram. So magnitude on the vertical axis, spectral class on the horizontal axis. And I've just put some red ovals there which show the domains of different types of stars like Cepheids, but that vibrate differently. This is all part of the history of astroseismology. I didn't put circles everywhere, but many of the white dwarfs are also oscillating. So that path that I've defined there by the red dot dashed lines is called the classical instability strip. And I wrote at the top, a number of distinct regions fall in this major region, which is called the classical instability strip. The Cepheids are the brightest stars there. Turns out the Cepheids have two types, population 1 and population 2. You have other types of pulsating star there. And here is a non-colored, simpler version of the diagram just to show the classes more clearly. So the classical Cepheids and the W Virginis stars, different population group. The Aurorari stars are fainter, and then the Delta Scuti stars are still on the main sequence, but they all fall in that path. But there are other classes. You can see that the top left, it speaks about beta Cephei stars, which have nothing to do with delta Cephei stars. It just happens that the constellation of Cepheus gave birth to two prototypes, delta Cepheids, which are evolved stars on the horizontal branch of evolution, and beta Cephei stars, which are massive, very, very young stars. 3 stars in the Southern Cross are beta Cephei stars. They're all very young. So I always tell people the Southern Cross wasn't there when the dinosaurs were around. It didn't exist. Those stars hadn't been born. So the poor things couldn't navigate in the south. Finally, yeah, there's not, oh, I'm just writing them right. So what are they? And this is where I get into the more scientific part of the talk. Okay, sorry, just observationally, they're all bright giants and supergiants. There's the luminosity range and the color range. But physically, we understand that these are essentially musical instruments. Look at these 4 plots of delta Cephei. It's now a bit stylized from the one I showed you earlier, but smooth. But at the top, you see what the magnitude does. There's steep ascent, slow descent. You can obviously simultaneously measure the temperature through the spectra by using simple black body laws of physics. You can infer the radius, and by basically just taking the gradient of the radius curve, you get the velocity. And on the next slide, I've drawn a vertical line which shows you in the 3rd row there, it goes to the point where the radius is a maximum. And you'll see that intersects the velocity curve where the velocity is 0. You can see the axis on the left, which makes sense. Those of you know calculus will know that the gradient of the radius curve is 0, there where the red line cuts it. So the velocity being grand must be 0 as well. And you can see it also coincides with the magnitude being between brightest and faintest, and almost with the temperature being the lowest. And if you just do a bit of simple mechanics on this, you realize that what we're seeing is a sphere that is expanding and contracting. Because of the laws of thermodynamics, when it's contracted, it is hottest. Because of the Stefan Boltzmann law, when it's hottest, it's brightest, even though it's smaller, because it goes as the 4th power of the temperature. So when the star is contracted to its minimum size, it is both at its hottest and its brightest. And when it's expanded to its largest size, it's at its coolest and its faintest. And that's what's happening. So you've simply got this expanding and contracting sphere, very regularly expanding and contracting. So again, from a physical, mathematical point of view, it actually pulsates like a harmonic oscillator. And some of the stars actually look exactly like harmonic oscillators, the classical harmonic oscillator that you learn about in physics. And that means that we could investigate whether these other types of stars, besides Cepheids, are also harmonic oscillators, in which case we could analyze their oscillations and learn about them. And it turns out, yes. So the beta Cepheids that you can see there, the classical Cepheids, the arrow on the right is for long period variables. You can see they're all very red and very bright. Those little gray areas, there's the delta Scutis as well. There are actually about 20 classes of pulsating star we know about now. So essentially 20 types of musical instrument. And some of them have similar characteristics, like, again, the ones there in the instability strip with the red borders. The upper ones are the Cepheids. You can think of them as the double bass. The aurolaries, the cellos, and the delta Scutis are the violins. They all are doing the same thing, but the delta Scutis are small, so they make the higher pitch, and the Cepheids are large and they make the lower pitch, but they're the same. So that's just a picture I found showing you the huge variety of musical instruments we use as humans: percussion, strings, brass, woodwinds, etc. And it seems like the universe has given us the same variety of musical instruments among the stars. So remember that I wrote some text in. The natural modes, eigenmodes, just the mathematically natural modes of vibration of a physical object depend sensitively on its composition, its form, and its structure. And therefore, the pulsation classes that we see represent particular stages in stellar evolution and also particular arrangements of internal structure. And the method of working out the interior structure and the rates of evolution of stars is called asteroseismology. And it has now become the sharpest tool, the most refined scalpel we have to learn about the interior structure and the evolution of stars. And that revolution occurred in the last 10 years, and we're almost there. I want to just tell you a bit more. This is to show you about the nodes. So for a string, it's easy. The nodes are points. You can put your fingers down on a string and hold it tight. If it's an air column, like in a flute or an organ pipe, there's a column of air moving in opposite directions. And the nodes, they are not points, but lines. The dotted line in the upper row of images show you where there are nodes in an organ pipe, for instance, or in a flute. And when you go to a three-dimensional body like a star, you get nodal surfaces, which are like the peel of an orange is a spherical surface. You've got the flesh inside, but the peel, if you take all the flesh out, you'll have the sphere, which is hollow. And the peel would be a spherical surface. And that's what we get inside the stars. We get these spherical surfaces, but we also get nodal lines on the exterior surface of the star. So these very nicely designed pictures by a group that's now no longer in existence, but in Vienna was a very strong group in Asteroseismology for many decades, show you simply how these nodal lines run. And you see there are little mathematical symbols saying m equals 0, 1, 2, and 3. For those who've done some chemistry and understand the periodic table, these are exactly the same m's that you use to define sp, d, and f orbitals. When you solve the quantum mechanical equations for atomic structure, you're essentially solving a wave equation, and the wave equation for a sphere that you solve to look at the electronic instruments is exactly the same equation you solve for the vibrational modes of stars. And so you get exactly the same mathematical solutions. But we don't call them SPDF, we just call them M is 0, 1, 2, and 3. We call them dipole, M1, we call it dipole mode, and M equals 2, we call it a quadrupole mode, etc. That's not important. But there are these fascinating details of oscillation. And there you can see successive shells. These are all nodal shells. So you can imagine that the dark orange lines are the cuts through shells, just like an orange peel. So that looks a bit like an orange, but presume that was the sun. And there are these many, or like an onion, many little surfaces which don't move while the sun is vibrating. The sun vibrates in about 1 million different tones as far as we can detect thus, or maybe more, but we can detect about 1 million tones in the sun itself. So it's an extremely complex, active, vibrant musical instrument. So those are just the spherical nodes you get as well. Here's a quick GIF of a particular mode. You can see it's an octupole mode with m equals 0, exaggerated in amplitude, but there are stars that do exactly this. The star is not being manipulated by anything. This is just a natural oscillation of the star. Like a blob of jelly on a plate, you poke it with a spoon and the jelly wobbles. What pokes the star? Well, remember, the star is generating enormous amounts of energy flowing from the core or from a shell in the star to the outside. So there's a lot of dynamic activity going on, plus all stars rotate. And so this happens naturally. And I'll tell you more about that in a moment. I must speed up a bit. I can see time is running more quickly than I thought it would. That's another mode of oscillation of the star. And that's just a diagram showing you how the waves move inside a star. There are two main ways, but I don't have to talk about that. It's pressure modes and gravity modes. For certain types of oscillation, a star is doing exactly what a four-stroke internal combustion engine is doing. When the material is compressed, like you can see there, when the piston goes to the top, one place the spark jumps, the other one the exhaust gases get expelled. A star does exactly this. When it's compressed, it absorbs heat, does work, expands the star, releases the heat when it's expanded, and then repeats the whole cycle. That's just a thermodynamic picture. Throw something in for everybody. So that's for a heat engine, a very basic pressure volume graph. At the bottom, you see the same graph for an Aurora Lyrae star, for a physical model of an Aurora Lyrae star. It's the same diagram you see at the top, but now the way it looks in an Aurora Lyrae stars, again, pressure volume. When the star's interior behaves like on the left, the oscillation, the perturbation is driven. You get a sound that lasts. When it behaves like on the right, it gets quenched, it gets suppressed. And so what stars do, like that flute and the violin I showed you earlier, each star has its own pattern of vibration modes that get damped and driven. And the sum total is what we hear. I think I'll go past this because I'm looking at the clock. The partial ionization zones are the zones in a star that drive the sort of four-stroke internal combustion engine type of heat engine behavior. What I'm showing you here is just that the whether a star will oscillate like this, in other words, generate the sounds associated. Remember, it's a vibration. It is actually a sound, but we detect it via light, not via air. Okay. Depends on where the ionization zones of hydrogen and helium are in the star. And so I'll summarize that with this figure. So there's that instability strip. On the left side, the star is too hot, and the hydrogen is already ionized at the surface. It can't act as a driver. On the right side, where it's red, these zones are too deep, and the inertia of the outer layers is too high. That also can't drive the star. So between the blue and the red line is this Goldilocks zone, where the star is just correctly structured to oscillate as a heat engine using the ionization zones of hydrogen and helium. That's what I wrote there, I just told you. Okay, now I get to the revolutionary part of astroseismology. Same picture you saw at the start. If you look closely, you'll see that on that tower where it's being launched from, it says Delta, that's the rocket, and below that says Kepler. How did Kepler's name get there? And you can see on the rocket itself, it says search for for Earth-sized planets. Bit of a misnomer. That was really the job of TESS later. But anyway, Kepler was launched in 2009. Designed as a planet-finding telescope, immensely successful. That this is from 2018, so the number of planets confirmed, not candidates, but confirmed, is now obviously beyond 2,662. But when it was being designed, some people realized this would be a superb astroseismology telescope. And so for people like me, the main job of Kepler was to teach us about the stars. So that's how Kepler works, in case you haven't seen this before. Look, there are two things happening. There's a planet transiting across that star, the little black dot going from left to right. And as the planet transits across the surface, because it blocks the star's radiation, what we see is a dip in the radiation that we detect. And depending on how long the star takes for the transit, that will take a certain time. Here's a real observation of the 8th planet orbiting a star called Kepler 90. And what I want to draw your attention to is how small that effect is. Look on the left, relative brightness. So without the planet, the average brightness of the star is 1. At maximum transit, it's 0.99990. Okay, so it's 1 part in 10,000 fainter. Now, detecting and the error bars on those purple dots is another factor of 10 smaller. So it's 1 part in 100,000. The final precision we got on observations of stars using the Kepler telescope was about 2 parts per million. 2 parts per million. So you could see a signal coming from the star with changing the starlight's magnitude by 2 parts in a million. So we start talking about micromagnitudes. What you see is a paper that I worked on in 2011 with my old supervisor, Louis Bologna, who's still working flat out. And what you have there, and I don't have time to talk about this in much detail, but it's called a periodogram. It's basically the counterpart of those flute and violin diagrams I showed you, where you see the strength of various notes. And these are detected notes in those 5 stars. You can see there. The dashed red line is the threshold for detectability before Kepler from the best telescopes we had on Earth, which means that everything on the next, okay, so as I'm showing there, it compares with the flute and the violin. It's the same sort of pattern, but the stars have hundreds or thousands of these little notes going on. And all the purple blocks were invisible from the Earth before Kepler. So for 4 of those stars, we wouldn't have seen that they pulsate at all. And for the other one, the second one from the top, we would have seen about 10 notes, but not the hundreds that Kepler showed us. So Kepler totally opened up our ability to hear the music of the stars by 100-fold. The number of notes we could hear increased 100-fold, and the number of stars we could detect increased almost 100-fold. And here's just one example of the amazing things we have learned using Kepler. So the bottom right is, okay, the bottom left is one of those periodograms, or if you like, sonograms of a particular star. On the right is a plot made of many stars. And you can see there's a plot on the vertical axis of a thing called delta P, and on the horizontal delta nu. That's a Greek N nu. And why some are blue and some are red? the Kepler telescope within a decade allowed us to look at a red giant star and know where exactly on the evolutionary track that star was physically, not because of its position on the HR diagram, but physically. Is it burning helium in its core? Is it burning hydrogen in a shell? Details like that. Unbelievable. So astroseismology has essentially exploded in its information content since 2009. Kepler observed that portion of the sky all the time until the one gyro ran out, and then it was repurposed and it observed stars along the ecliptic, but less intensively. So for 4 years, it observed that patch of sky crossing over Lyra and Cygnus almost without interruption. And that allowed us that 2 parts per million precision. But that was a limited part of the galaxy. So TESS was sent up in 2018, 9 years after Kepler, to look at practically the whole galaxy. TESS is the Transiting Exoplanet Survey Satellite. There's a picture of it. And this is on the NASA site, dated 21 March, passing the 5,000 confirmed planet threshold. And more than 4,000 of those 5,000 planets came from Kepler or TESS. So that's as an aside, but what they've done to astroseismology is astounding. So for the people with deeper insight and knowledge here, here's the delta nu I spoke about earlier. Until Kepler, only the sun showed us a sonogram like this. What you see there is a plot of period against frequency. The horizontal axis, it runs in microhertz. So obviously, a frequency of a microhertz corresponds to a period of 1 million seconds, which is about 12 days. So 1,000 microhertz is about 12 days divided by 1,000. Okay. So these are on the order of oscillations of number of minutes. So they're very rapid oscillations on these stellar surfaces. It's like ripples on a pond, but they are physical oscillations like those in a musical instrument. And all these spikes are actual different notes. They differ in amplitude. They make that pyramid-like structure. And they're regular. So there is a thing called delta nu with a large delta in red, which you can see indicated at the top. And there's a thing called small delta nu in green at the bottom, which is the tiny separations you see there. And what you see on the right is based on decades of extremely hard work by very clever people, how those things you measure by observing these stars photometrically very precisely, how those things tell you about the interior structure. The first equation there says delta nu, capital delta, equals the inverse of the integral from the center of the star to the edge of dr over c, where c is the speed of sound. The speed of sound changes every millimeter in a star because of the interior structure, because of the pressure, the density, the temperature, the composition. So if you have a model of a star, you will only match the observations once your model is so good that the speed of sound that you calculate matches that delta nu. At the bottom, you've got a more sophisticated equation for the small delta nu. The point being that the most wonderful things that happened. Here you see 4 stars like the sun. Again, until 2009, no one had seen any graph like this except for the sun. Here are 4 sun-like oscillators, different ones. You can see the names are there. Never mind the names. But from bottom to top, you see the yellow arrow says age. This is what's going to happen to the sun as it gets older. As it gets older, it's going to get larger and cooler. It's going to go from a violin to a cello and then to a double bass. And you see the sound pattern moving to the lower pitches. All of those spikes are real. The thick black rubbish is the noise. That's at a few micromagnitudes. But there are 4 sun-like stars way out in the galaxy, maybe 1,000 or 2 light years away, and we can see these notes. So what we are able to do now with our understanding of stellar structure and evolution is really astounding. So that was the current state of play. TESS is still working and more data are coming in. TESS will eventually also stop working. So this is a test for those of you who know about space telescopes. Do you know which ones those are? I think the one bottom left, most people will know, but here are the answers. So that is obviously an artist's rendition at the top left of Kepler. Top right, that's what TESS looks like. And Kepler is now dead. It's in solar orbit, by the way. It's not in Earth orbit. Very similar to the Earth's orbit, but not quite. So it's falling a little bit behind us the whole time. Eventually we'll catch up with it, but not quite in our orbit. well, TESS is in a very elliptical Earth-centered orbit. So when it's at the perigee, it downloads all the data, and when it's the apogee, it's very good at observing. So it has this very eccentric elliptical orbit around the Earth. So all the data downloads happen at perigee. At the bottom right, of course, is the James Webb, which is newly up in the sky doing wonderful things. And that's especially going to look at the atmospheres of some of the planets. Obviously, it's an infrared telescope, the atmospheres of some of the planets that TESS is finding. But the real successor to Kepler and TESS is at the bottom right. Kepler and TESS were mainly NASA-driven missions, but Plato is an ESA, European Space Agency-driven mission, due for launch in 2026. We'll see what happens. And that is going to build further on the wonderful work that Kepler and TESS have done. So I could have gone on for another hour, but I've been at it for more time than I think I would have. It's probably 48 minutes. So I think I'm going to stop here then, which was my last slide. And I'm very happy to take any questions. I've given you a really quick whistle-stop tour through where astroseismology came from, what it means physically, why it's so important, and what we're busy discovering. I hope you find it interesting, and I will now be happy to answer questions. Thank you.
Wow, that was fascinating and an enormous amount of stuff packed into 40 minutes. I think it could have easily gone on for 400 minutes, probably. Thanks very much. It was fascinating. I learned a lot. And I'm going to go back, and I'm glad I'm recording this. I'm going to go back and watch this a couple of times, I think, to properly absorb what you're talking about. Okay, anybody got quick questions for Chris? Pierre, Peter, all the experts?
Anything. There's someone once said there are no silly questions, only silly answers. I'll do my best not to give you a silly answer, but any question is welcome.
Peter Harvey's got his hand raised. Would you like to go ahead, Peter?
Yeah, I would just like to say, and I'm sure that other people will agree, that I think that was quite, and I know this is an objective judgment, that was quite possibly the most remarkable presentation that I've had a pleasure of sharing with my colleagues. And it could have been twice as long and I'd still be awake. And I think that's saying something. And I thank you very, very much, Chris, for a wonderful presentation.
Peter, I'm so sorry. I have this Zoom issue at the moment. Only on Zoom calls, my loudspeaker struggles. It can't be the hardware because it doesn't happen anywhere else. And I only picked up almost only a few words. I'm so sorry. Is it possible to summarize what you, it just happened. I'm so sorry. It just comes and goes. It's a Zoom thing. I didn't hear what you were saying. I'm sorry.
Sorry, Peter.
The most remarkable presentation I've had the pleasure of sharing with my colleagues.
I wonder if I'm gonna escape quickly and just see if stopping the share will help. Now, very embarrassing that I can't hear. Otherwise, if you quickly want to write it out, but let's try one more chance on the sound. I'm just going to close everything that I've got. Closed everything on my laptop except this. Can we give it one more shot, Peter? I'm so sorry. I do apologize.
Okay, sorry. I hope I'm not boring, Mother. I just
now I can hear you.
Very, very briefly. Can you hear me now?
Now, yeah, I closed everything on the computer now.
Yeah, I think that was the most remarkable presentation I've had the pleasure of sharing. And it could have been twice as long and I'd still be awake. And that's something for me.
Oh, that's music to my ears, Peter. Thank you. I could talk for a few hours on this because I've been doing this for 40 years, but thank you. Wonderful. Thank you.
Yeah, all I can say, I'd like to repeat as well what he was saying. And I think, you know, there's a lot more I'd like to know about what you're talking about here. I could probably, I've got sort of 100 off questions, but I can't sort of focus on one particular question at the moment. I think I'd just like to know a lot more about your subject and understand.
Thank you, Derek. What I could offer is do a follow-up next year where I zoom in on one particular aspect. It was totally comprehensive, you know, 45 minutes to try and say enough about the topic that people knew what it was about. But I could easily focus on a particular topic and do a talk on that only. So I'll be happy to do that.
Yeah, that would be great, because I think there were probably several aspects where I would have liked to have stood still and ask questions, but it would have just taken too long, I think. So yeah, let's do it that way. Let's have another talk in the future.
We can canvas what people were interested in, and then I can design something around that, because yeah, this is really just scratching the surface, I promise you.
Yeah, thanks. All right, I've always wanted to actually know more detail about Cepheids and how these things work and all these things. Now I've sort of gained a small insight. I'd like to know more now.
Now, as you can hear, I'm very passionate about this. I know it's been it's something I've devoted a lot of my time to, my life to. So yeah, I'm happy to talk about it. And you're right, it's there's so much fascinating information coming out of this. I mean, one thing that I once gave in a public talk, I just hinted, I couldn't explain the detail, but that apparently some white dwarfs have diamond cores because of how they oscillate. And the only way they can oscillate that way is if the carbon is in an sp3 bond, which is what diamond is, not graphite. So stuff like that comes out of this.
So sorry, just explain to us. That's I've seen sort of headlines somewhere that there's diamonds, a lot of diamonds in this, but I never read the articles. I just thought I was. So again, how can they tell that there are, obviously they can tell that maybe there's carbon, but how do they know there's diamonds? I mean, that's
again, it's from the oscillations that the only way that you can get those notes is if the carbon core is in an sp3 bonded. I mean, it was a major paper 20 years ago or so, and there were some follow-ups. But I can give a talk on that, for instance, or as part of a talk. The point I'm making is that the information you get out of this tool we call Asteroseismology is phenomenal.
Have you had any phone calls from De Beers asking you where are the most diamonds and how quickly will we get?
No, they said please stay away, because there's so much in there that it would totally destroy the price of diamonds, because they wouldn't be scarce anymore.
Okay.
Yeah.
First, I want to share Peter's sentiment. That was absolutely fascinating. I think one has read or seen or heard quite a lot about Kepler and TESS, but I think it's mainly been about the visual images and the determining the size visually, and also from analyzing the spectra. I never realized before, until this evening's talk, that you can learn so much about the structure of the stars. That, I suppose, displays the depth of my ignorance, but thanks for enlightening all of us.
No, most people don't, Pierre. There are a few, there are about 500 people in the world who do astroseismology, and outside of that group of about 500 people, almost nobody knows this. So don't feel alone. Okay.
The nearest I ever heard to something like that, and excuse me, I'm in Cape Town, so I hope I'm coming through, was a lecture we had, and I think it referred to primordial sound that we were listening to, and they played us the sound that came almost from the Big Bang time. Was there any oscillation there or any relevance from what you said?
It would be similar. I mean, I'm not 100% sure, but I know there's an oscillation spectrum that became very famous after COBE and the WMAP satellites that, of course, probe the microwave background. The current concordance model of the universe has these, almost like I showed you with the stars, and I showed you those nodal lines, and I spoke about dipole and quadrupole and octupole oscillations, that there's something of a similar kind in the large scale structure of the universe, where the voids are, where the galaxy clusters and superclusters are, that there's a pattern. There are scales, and they've related that in a way to frequencies as well. So I imagine that what you're talking about refer to that. But it's what I started with. It's patterns, it's numerical patterns, and sound is simply a numerical pattern. So and you can call the sound, the fact that the human ear can only hear a small interval, just like a human eye can only see a tiny sliver of the electromagnetic spectrum. our ears can only sense a tiny sliver of the spectrum of the vibrational spectrum, but it doesn't mean there aren't others. So, yeah.
Thank you. That's great. And any link to the Fibonacci code, like where you get the 258? Does that happen with that sound too?
I haven't seen that, except of course in the spiral structure, which, as far as I understand, is a growth phenomenon. So everywhere in the universe where something grows organically, like we see in snails and in sunflowers and in spiral galaxies, it is something to do with efficient growth that gives that, which I think is related to the Fibonacci sequence. I think, I'm not 100% sure, but I think that logarithmic spiral, the golden ratio, is linked to the Fibonacci sequence. I think so. I'm not sure.
Super. Thank you very much. It was a fantastic presentation.
I'm happy that it was. Thank you.
Chris, thank you very much for a very entertaining talk. I really enjoyed it. I just have one question. Is there any reason why you are seeing actually a normal distribution of all the frequencies that you detect in a star? Because I look at the plot that you show, it looks like
yes. You see, that's the eye of a scientist. You see, is a Gaussian distribution there, or normal distribution. Yes. You have me on the spot. The stars I worked on are not solar light. I worked on those very hot stars, the beta Cepheids. I can tell you lots of stuff about them. But all I know about solar oscillators or what I've heard in conferences and so forth. So there is an answer to your question, but I don't know what the answer is. So I have to go and look and maybe email you an answer that you can share on the group. But the honest truth is, I don't know why.
No, thanks a lot. Just another one. Now that you've committed yourself to another talk, can I put this for next year's presentation on a topic of your choice?
Can we do it at the same time? I teach
yes.
very intensively from February to August, and that's why this year I chose September, because it's
yes.
difficult to do justice to this when I'm up to my ears in teaching. So
excellent.
We do it again same September. Great.
Okay. Thank you so much for that, and I'll keep in touch because there's lots of things that interest me from a personal point of view, but I don't.
Yeah, you're welcome.
Discuss it on this forum at the moment.
Yeah, you can email me and I'll give you my phone number and we can chat. Yeah.
Yes, thank you very much.
Okay, it was a pleasure. Thank you for the chance. I love talking about these things. It was great having a good audience. I appreciate it. Thank you.
Well, Derek seems to have vanished.
Sorry, I had my mic muted, but go ahead, go.
I just want to say thank you. That was absolutely fascinating, and looking forward to more of it next year. And good night to everyone.
All right, thanks everybody for attending, and thanks for a great talk. Much appreciated, Chris, and we look forward to more next year. And we'll try and do our homework before the time. All right, thanks very much.
Good night, everyone.
Night, everybody.
Good night.
There are no more questions, by the way? Oh, he's gone? Oh, he's gone. Okay. Cheers, everybody. I'm going to log off then.